colleagues, I start.
Okay, so that's it.
Yeah, okay, we can start without any introductions this day. I think it's
okay.
on.
Sure. So I take the following of yesterday's lecture, the follow-up, and I repeat some of the last slides I have shown, because this goes now into the type of chemistry we have been doing mostly in recent years, or not so recent. It started in the year 2000 or something like that, so it's not so recent, but it's still some chemistry which is very much developing. So first of all, it comes from the following fact. Yesterday, I showed you what was the origin in terms of the inspiration which can come from earlier work, and now we will go into it directly. So, as you know, supramolecular chemistry can be considered as a dynamic chemistry because the intermolecular interactions, non-covalent interactions, are quite labile. So this makes possible the rearrangement of the components, the dissociation, reassociation, and so on. And this is maybe called the dynamic non-covalent chemistry. On the other hand, one can also think of introducing into molecules similar dynamic properties. That means making molecules which are able to dissociate and reassociate. And this can happen if the molecules contain reversible covalent bonds. And this can be then defined as a dynamic covalent chemistry. If you want to put both types of dynamic chemistries under the same heading, the same umbrella, one can say that it is a constitutional dynamic chemistry where the chemical object, either covalent or non-covalent, molecular or supramolecular, is subject to dissociation, rearrangement, associations, sequences. And of course, because of this, in the course of the reassociation, it can change its constitution. That means undergo adaptation if there are specific stimulations of physical nature, like heat or pressure or something else, or chemical effector. And this then leads to the field which is now mainly our main interest, adaptive chemistry. Now, what is this good for? Is it good for anything? So what are the advantages? First of all, this constitutional dynamic chemistry, CDC, generates libraries, sets of entities, which represent the different combinations of the components. It generates dynamic diversity of either supramolecular or molecular level, and it enables also selection processes which are determined by recognition patterns and recognition type of interactions. What is it good for? It could be interesting for searching for biologically active substances. Why not also nano devices which can be made dynamic? And also, of course, materials which can also be made dynamic, such as dynamic polymers. This type of approach merges two very powerful technologies or features. On one hand, generating diversity results from a recombination of the different pieces, so it's combinatorics, generating diversity. On the other hand, recognition is based on molecular information, so it's a sort of an informatics, and this is two facets of chemistry which were, let's 30, 40 years ago, one did not speak in such a way about chemistry. Now, what type of dynamic interconversion processes do we have? First of all, on the supramolecular non-covalent level. Of course, there can be, this is just schematic here, there can be electrostatic interactions between an anion and a cation, for the carboxylate and an ammonium. Of course, also others. Hydrogen bonding is a very important one. Hydrogen bonding between, for instance, the NH of an amide and the oxygen of another group, or it can be simply an oxygen of an ether or something. Donor-acceptor interactions between electron-rich and electron-poor type of groups, and of course also metal-cation coordinations, which you will see again. On the other hand, what about reversible covalent reactions? If we want to develop non-covalent dynamic chemistry, molecular covalent chemistry, we have to look for reversible covalent reactions, like formation of imine double bonds from a carbonyl and an NH2, or acetal formation by addition of an alcohol on a carbonyl, or transacylation, also aldol formation, where the condensation occurs as to the aldol condensation, you know that, all of that. Disulfide formation, which can, this is interesting because that's a redox reaction, and here we need to have something outside which oxidizes or reduces, because you go from left to right by oxidizing, and from right to left by reducing. Metathesis reactions, shown here, boronic acid, Diels-Alder, Michael reaction. I call here self-contained processes, the processes with a star, they have in the starting materials and in the result, in the product, the same atoms. All atoms are present at the beginning and at the end. For instance, if you do that, an imine condensation between a carbonyl and amine, you lose a water molecule. But in this with a star, you lose nothing. You just get things together, and you just keep the atoms which were present in the starting materials. Now, let's have a look at one emblematic type of reaction, which is the condensation of an amine with a carbonyl group to lead to different CN double bonds entities. They can be imines, simple imines, as you see here. And this is a very important one. Of course, A can be of different types, and this can then lead to different types of rates of exchange and of combination and of heat hydrolysis back. Acyl hydrozones, these are derivatives. They have also an NH2, but they come from a hydrazide. A hydrazide is a compound from a carbonyl, from an acid, a carboxylic acid and a hydrazine. They can also then connect and make CN double bonds. So all these type of amines, they are, in addition to that, are simple hydrazines. They are also hydroxylamines and so on. They have different kinetic and thermodynamic features. Here I show you the father of this imine type of chemistry, Hugo Schiff, who is the person whose name is given to Schiff bases, condensation of amine with carbonyl. Here he is in his last lecture. I show you now the lecture room, the last lecture when he was at the University of Firenze in 1915. This looks very different from a lecture room today. Today, people have become so cautious. So I think it's incredible that you're doing chemistry in a lecture room. This is not allowed anymore, which I think that's incredible. It's really, why not? I mean, and here we have good old Hugo Schiff doing his experiments in front of the students. It's an interesting picture, I think. Now, this acyl hydrazone group I have mentioned is of special interest, although I will not use it very much, but it is of special interest because it has two interesting features. On one hand, it has two different types of groups, an amide and an imine, which provide the amide with hydrogen bonding and the imine with reversibility. So this is a very interesting feature. And you can also see that this is like a peptide bond, and there's a peptide bond, and the imine next door, just nearby, will provide dynamics to this type of compound. So acyl hydrazone derivatives are indeed very interesting to use for covalent dynamic chemistry, because they unite these two features of having an amide group of hydrogen bonding, a peptide bond in that respect, and also reversibility through the imine function. Now, before I go more detailed into it, we also use this covalent dynamics for producing motion. This was rather surprising that nobody had done it before, because it's so simple, as you will see. How can we produce motion in covalent dynamics? Very simply, if we now take this compound, these imines, if we have simply salicylic aldehyde and diamino and an ethylene diamine, this is extremely simple. When you mix that, of course, you form an imine. Now, if you mix it in 1-to-1, of course, you have not only a monoimine, you have also the diimine and the zero imine, but nevertheless, the monoimine formed can form on one nitrogen or on the other one. And there is no reason why one should prefer to the other one, because it's symmetric. So what happens is that the imine, the carbonyl, which makes the imine, can walk to the other side by forming an aminal. This is like taking a step. Here we have the two legs together. You open the legs, you take a step, and you close them on the other side. So this is, of course, not directional, but it's a very simple process which I have studied. And I was amazed, very amazed, that nobody had done such kind of things before. It's producing motion by the simple imine walking from one nitrogen to the other one. Of course, the rate at which it walks depends on the distance between the two nitrogens. It is relatively fast when it's just ethylene diamine, and it gets slower and slower when the two nitrogens are further away. So this is a dynamic covalent motion in what you may call aminal steps. Now, one can extend it by taking polyamines, where the same happens, where one can show that a carbonyl group connected on one side can walk to the other side. But this is non-directional motion. It is what you may call a minimal walker, a minimal system, very simple one, of having an object, a molecular object, walk on another one, and it's driven by Brownian motion in aminal steps. Then the question is, can one orient the track? Yes, one can. If one synthesizes a molecular track, an imine track, where one nitrogen on the left is more basic than the one on the right. So in this case, when you have here the carbonyl forming on the amine, which is the more basic, then when you add acid, of course, this one is protonated fastest before the other one. And so this compound shifts over to the other side, and you can shift it back and forth by adding acid and then adding base. Now, this can be done also on a surface, and Petr Kovaricek, who was my doctoral student from Czechoslovakia, from Prague, he also then developed it on a surface in the following way: a surface containing, presenting amino groups on this here, you see. And he used a fluorescent nanoparticle, which was derivatized with a salicylic aldehyde, something of that kind. You get here, you get then a motion, they bind together. And when you, of course, when you have acid on one side and base on the other side, it will walk from the acid side to the basic side. And this is quite normal, because protonation, of course, destroys the imine. And so you can have this thing walking over there. And if you change then the orientation, basic on the right-hand side and acidic on the left-hand side. Then it works back. Okay, so this we have just seen. I wanted just to point it out again to remind you of it, and we have now seen what we can do with it. So first thing, what can we do with biologically active compounds? How can we search for biologically active compounds? Suppose we have a number of components of different structures, different shapes, and different atoms, different molecules, so to say. But they have all of them attached to them a functional group which can undergo reversible reaction. So this thing then generates all possible combinations which result from the connections between these components. And it generates a dynamic combinatorial library or dynamic covalent library. It's combinatorial by principle. It is covalent because they're reversible covalent bonds. And this generates then the whole space of all possible combinations of these components you start with. Then the question is, what can you do with it? What is it useful for? You can simply use a basic law of thermodynamics, the Le Chatelier principle, which is the following. You add a receptor, and if among these constituents here, there's one which binds well to the receptor, then it will be amplified. It will be amplified because the receptor will select the combinations which bind best to its receptor site, which means that there is a selection of the best binder, which is amplified, and we may say that the log assembles the key. This has been used for searching for best binder, especially in biology and in medicinal chemistry, and leads then to the possibility of having a new approach to drug discovery. It consists of an adaptation of the dynamic system to the receptor site. So let's have a look at some of them. I take as a first example, I will show you two examples of that. Take as a first example one which is based on carbonic anhydrase, the enzyme which exchanges CO2 water with carbonic acid, very important enzyme in our lungs. This enzyme has been extensively studied and inhibitors have been found. For instance, a very good inhibitor is shown here. It has a sulfonamide group which attaches to the active site on the zinc in the active site. And it has also amino groups. It has also lipophilic groups, the hydrophobic wall, which then can bind with this benzene group. So in other words, the two main features of the active site of this enzyme, the zinc atom and the hydrophobic wall, they form the points to which the inhibitors can interact. This is a very good inhibitor. It's 1 nanomolar. So what can we do? Just to illustrate the principle. Of course, this compound has no dynamic features really, because the amide is not an imine, but you can replace the amide by an imine, and hoping that it's reasonable that the replacement of this amide by an imine will be a small perturbation compared to the strong interactions of the sulfonamide and the benzene group with their binding sites. Here is then the library you can set up: 4 amines, 3 aldehydes, 3 times 4 is 12 constituents, and one has, of course, to be careful to put in benzylamine. As we know, then benzylamine is important. And so we get these 12 constituents, where the one down on the right here is the closest structure to the very good inhibitor we have seen earlier. This is a very good inhibitor on the bottom right. And this is among the 12 constituents, the one which is closest to this interesting compound and this strong inhibitor. Now, if you now look at the library of the 12 compounds and look at just 2 peaks, we select 2 peaks, you find out that we can choose this one, which is the one which is very close to the good inhibitor as a peak, and the another one which has a component in common, this sulfonamide, and the two have about the same fraction, the same ratio with respect to the total amount of constituents. So if we now compare these 2 constituents in absence of carbonic anhydrase, they are about the same intensity. And if now we add carbonic anhydrase, you see that the one which is closest to the good inhibitor is amplified with respect to the other one. And this is very informative because it tells you that you can then use that the system wants to show you that this constituent, this of the 12, is the one which is a good inhibitor of the enzyme. And it means also that there's an adaptation of the dynamic system to the addition of this biological effector. So it's a proof of principle that indeed the system works the way we think it should work. Let's have a look at another case which is more complicated. Concanavaline. Concanavaline A is a lectin. That means a protein which binds sugars, and this lectin, it has as sugars, it has mannoses as sugars. Concanavaline has a binding site which can complex 3 mannoses. So what can we do? We can now set up a much more complicated library. Maybe we have here 6 sugars, 6 different sugars, and they come all from all of them bear benzaldehyde with an oxygen, but they can come from the derivatization of different kinds of sugars. On the other hand, you also use then a single hydrazide, a double hydrazide, and a triple hydrazide, and then you mix the whole thing. Now, this is now much more complex because you now get 690 constituents. How can you then analyze the system? You can analyze the system in the following way. You can do dynamic deconvolution. What does it mean? This is, of course, you could probably also add physical methods that could analyze it and so on. But this dynamic deconvolution means the following. You look at your library and you remove from it one component. Then the whole library rearranges and generates all the constituents but not the ones which contained that component which you have removed. And so if the removal of a given component produces no effect in the properties of the library, then it means that that component was not important for what you are looking for. On the other hand, if the component has a very strong effect on the result of what you are doing, that means, for instance, interacting with a receptor site, then you know that that's a strong effect, has an important role in the interaction of the sugar with concanavaline in this case. So the control series indicates that there's a strong effect here, and this is this is the blank. So you can see here when you remove 1, 2, 3, 4, 5, 6, 6 gives a big change. So 6 is an important component. And then when you look to the amine groups, then you find that J, G, and I are important too. So what are they? In fact, this is mannose, and we know that concanavaline wants to bind mannose, and here there are 3. So we know also that concanavalin does bind a trimannosite, 3 mannoses. So this experiment is very simple. It shows you one important thing, that concanavalin binds mannose and binds 3 of them. But doesn't know exactly what is the best disposition and so on, but it gives you a lead for finding out better compounds later on. Now, can one also make nanostructures which are dynamic? And let me just illustrate that, but by one example. If you take this hydroxylamine, this phenol hydroxyaniline, hydroxyaminophenol, if you want, you can call it as you wish, and have with a water solubilizing group, a SO3-. If you mix it with this pyrimidine, which has 2 aldehydes, then they can react, generate here between this NH2 and this carbonyl, generate an imine. And when you mix these 2 things in presence and with addition of cobalt or zinc, you get immediately from just from these 2 building blocks, they go together, they make everything needed to form now the ligands to form this grid. You can see this red ligand in front. You can see that it has 1 molecule of this sulfonamide on the side here, this aminophenol here, and the other one here. And this gives this ligand, which is shown in red. So it is a 2-level self-assembly, because you have first to connect these 2, and then you have to build up with metal ions, the grid type of complex. This is also interesting in terms of driving the system to form this grid complex. Suppose now we take 3 different carbonyl groups, this one, and we take 5 amino groups. This gives a set of imines, which recombine, which exchange. And then when you add metal ions, they form very strongly this grid complex 2 by 2. This, by component selection, you can see that among these different components, only 2 are selected, the dialdehyde, of course, but also on the amine side, the one which has the best, which leads to the ligand, which has then the best gauge-forming processes. And you see here that this library, which contains a dynamic set of imines, a mixture of imines, as soon as you add metal ions, which can form a grid, it will simplify the system and give only the imines which are necessary for making the complexes. Now, what about materials? Materials are quite interesting, and they open new avenues of development. First of all, let's look at the category of materials which are polymeric materials, dynamic polymers. We call them dynamers, dynamic polymers, reversible polymers which are able to undergo exchange of their components. One can distinguish 2 categories. First of all, molecular covalent dynamers, where monomers having here functional groups at each end, which undergo a reversible reaction. The yellow with the red forms a reversible reaction. And this then leads to a main chain, a polymer, where the monomers constituting this polymer are then reversible. So this yellow and red is reversible. It can dissociate and reassociate. See, these are covalent dynamers. On the other hand, if the end groups of the monomers are interactional, that means sites for supramolecular interactions, then it forms this kind of recognition site where the red and the yellow are complementary interactional groups. So these are then non-covalent dynamos or supramolecular dynamos. As you realize, supramolecular dynamos are by essence dynamic, and they are present because it's supramolecular type. However, the other ones, the covalent dynamos, they have to be intentionally made by intentionally introducing a catalyst and introducing groups which can reversibly connect and dissociate, like imines, like polyimines. We will come to that. Let's first have a look at a supramolecular polymer chemistry. We did that many years ago. It was in 1990. And this was interesting. I cite the date because you will see in a moment it is a very important date for some results. So what did we do there? We took a spacer derived from tartaric acid, which was derivatized with a long chain C12H25 on the OHs of tartaric acid. And the carboxylic groups of tartaric acid were condensed by ester formation with AB, with here, as you can see, a DAD, donor, acceptor, donor, hydrogen bonding. The complement to this is this one, which you see here, where you have now a section, a pattern, which is acceptor, donor, acceptor. Of course, acceptor, donor, acceptor is the reversible, the complementary group of this DAD. So if you now mix these two, the DAD and the it's a uracil type, ADA, then you find this one. You find that a chain is formed, you see here, a long chain can form due to the formation of 3 hydrogen bonds, which links the monomers together. So it is a supramolecular chain. It is not a normally covalent chain like one has in common polymers. It is a supramolecular main chain polymer. Note also that the starting materials, the starting components are solids, and when you mix them, you get a liquid crystal resulting from the interactions between these two monomers. This is just an electron micrograph, which you'll see others. I would like to point out also that that's a nice example of an emerging property being generated. The two solids, when mixed together, give a unit where we have now a long chain with a main chain supramolecular polymer and the liquid crystal, and this emerging property is the result of simply mixing two solids. Now, let's see that in fact, it's not so simple. It's even more complicated than that. You see here, molecular components here, which this is a starting material. Then they can associate and give supramolecular polymer chains, as shown here. But that is not finished. This is the first step, where you get a supramolecular main chain polymer. But when you study them by X-ray scattering, you find out that in fact it's more complicated. That there are 3 of these strands which wrap around the axis of a cylinder and thus generating a triple helical strand. The long chain C12H25 they stick out of the strand. In the center of the strand, you have the nucleobases and the aminopyridine, which I have shown earlier. The diameter is 15 angstroms in the middle, about 15 in the middle, about 50 outside, 40, 50 outside. And you can then do electron micrographs, and you find that indeed, you see, the diameter of one of these fibers, I haven't put any measurement, but the diameter of these amounts to about 40, 50 angstroms. And you can see how they connect together. What happens here to make the fibers is that the side chains probably, they entangle, they do this, they entangle so as to attach to one another. And these fibers, you can see immediately that if this is about 40 angstroms, these fibers are very long. They're really nice polymeric, supramolecular polymeric fibers. These are also, you note, three levels of hierarchical self-assembly. It's a sequence of self-assembly, and therefore there's a sort of a self-organization process which leads from the nanoscale to the microscale. Now, I mentioned that we proposed this concept of supramolecular polymers in 1990. Then it happened that after proposing that, of course, many people began to work on these supramolecular polymers. And in 2023, a small company from the Netherlands had made biocompatible polymers, which were used for application as cardiovascular implants. This was then used for the surgical treatment of children which had a severe cardiac malformation and which required reconstruction of the heart. It was done in 2013. That means 23 years after introducing the concept of supramolecular polymers. And here you see the little girl, Dominika, which was operated by Leo Bokeria from the Bakulev Scientific Center of Cardiovascular Surgery in Moscow in 2013. So this was, of course, a very nice demonstration that research which had started with nothing else than just basic research, thanks to the fact that a company, Xeltis, from the Netherlands, Xeltis company was thinking that this could be very interesting for medical applications. And then, of course, you had to find somebody who was ready to do it, which is shown here. Now, there are many children have been treated, and now the company has also developed pulmonary heart valves, which have been implanted in Budapest, in Krakow, and in Kuala Lumpur, and also in children. Of course, heart valves are now more complicated because they have to move, whereas this little girl had a problem of a single ventricle, if I remember correctly, a single ventricle of their heart. So the heart had to be have a separation, which was then a separation made up of these polymers. I am told that that's a breakthrough in surgical practice, and the company is now developing it further for other applications. Another property of interest for supramolecular polymers are the possibility that they can have a self-healing feature. If you take here this very nice transparent film, which was made by one of my Indian postdocs, here you see his fingers, and the film was very nice. And somebody then cuts it with the scissors, and then you superimpose the two ends. You press in the middle here, you press with your finger at that point, and you can stretch, it sticks. In other words, if you cleave this film, you superimpose and you press for a minute or two, you get a repaired film. The film is repaired. So this is also a very interesting property of supramolecular polymers, because they can lead to many applications. These are just technical details. Now, what about, these are supramolecular dynamic polymers. Now, what about covalent dynamic polymers, covalent dynamers? Dialdehyde with diamine leads to polyimines. Dialdehyde or dicarbonyl with dihydrazine leads to polyacyl hydrazones. And this, I have already insisted on the intrinsic property of this type of sequence, the acyl hydrazone type of units. Now, what can one do with it? Let's first look at the polyimine dynamer film. If you take a dicarbonyl with a diamine, you can make a polyimine, okay? And this polyimine gives then a nice film. It has been done in collaboration with a Japanese company, Mitsui Chemicals, which was sending to my group co-workers from their research center for studying. They were interested in this possibility of the possible functional and applications, functional properties and applications of these dynamic films. So they were sending co-workers to my lab. They were doing the research here, and then they went back to Chiba, where they have their application center, to the research application center to try to develop it. So they made very nice, this is a very nice film, as you can see. They made about 300 kilos of it. And this film is a film which can be degraded. You may call it green plastics because it has two degradation processes, which I show here. The film consists of a polymer, a polymeric film, which has a biodegradable section and imine bonds. So when the film gets into the environment, the first step is the degradation by hydrolysis of the imines in the environment. And then the second step is the biodegradation of the middle point here, the section which is the biodegradable polymer. So it's a double degradative film, double degradable film. What is it made of? It is made of a polyester moiety and of imines, which give the dynamic properties. The polyester is the biodegradation one, and this is the other one, the imines. Okay, there are mechanical properties. I don't want to insist on that, but I would like to show you to illustrate that. The film without imines, this polyester film without imines, this does after 6 hours in water has no degradation. The molecular weight is about 97,000, no change, no degradation. When you now introduce polymeric centers, imine centers in this polymer with molecular weight 6,300 between the imines, then you can put it again in water. Then you observe after 6 hours a slight disintegration. And finally, if you have more imines, a higher density of imine along the chain, of imines along the polymeric chain, then you have a complete disintegration after 6 hours in water. So you see, you can regulate the degradability, the rate of degradation of these polymers by simply changing the number of imines, the density of imines, let's say, in the film. So water disintegration rate can be controlled, and that is, of course, a very interesting property. For the moment, the compound was still too expensive for companies to develop applications with it. But I think with the need now more and more, there's more and more a need for going to plastics which can degrade rather than plastic bags, for instance, which are not degradable. This would be, despite the fact that they are somewhat more expensive, this would be a very good way to make, for instance, plastic bags for supermarkets, which can be degraded in the environment. Here is now this polyesyl hydrazone. Now, not just the ethyl hydrazone groups, but the polyesyl hydrazone, where I point out that thanks to the presence of this amide and imine, on one hand, we can think of making dynamic biopolymers, because this is a peptide bond, this CONH, dynamic biopolymers. And thanks to this unit, this imine, one can also make one can make them dynamic. So this is either on the biological side, biopolymers, which are dynamic, or on the materials side, dynamic polyamides. For instance, making nylon, but a dynamic nylon, a nylon which has imines in addition to the normal nylon structure. What can this, so let's see what are the properties which are brought in by the fact that these dynamers are now dynamic. What can we do in addition to what normal polymers do? Suppose we make two different films of these polyimines. One film consists of A, let's say the dialdehyde, B, let's say the diamine, which then makes a polyimine, AB, AB, AB. Then you make another film which has A prime, another dialdehyde, and B prime, another diamine, and you make A prime, B prime, A prime, B prime. Now, you superimpose these films. What happens? What can happen? First of all, remember that the connections are dynamic in the whole polymer. And then what can happen is that if there is a disconnection somewhere, it can reconnect somewhere else. So the starting polymer has AB, one of them, the other one A prime, B prime, constituents. But there are two other ones you can make, A prime B and AB prime. That's exactly what happens. If this bond breaks, and another one down here also, you can then generate A B prime and A prime B. So you have 4 constituents, which may now be interesting because we have an interesting property, because why not? One of the new combinations, AB prime or A prime B, may have a feature like having new mechanical properties or optical properties of interest. Let's have a look at these 2 features. So if we take at the start this very soft and stretchy film, this is and intentionally make very soft and stretchy. It has dimethyl siloxane units, and it has here ethyl hydrazone units. So you see here, this polymer gives a film which is very floppy, very soft, very stretchy. It has not good mechanical properties, much too soft. Then you can take what you may call hard monomers, monomers which are more rigid, and add them to this film in increasing quantity. You introduce these because these bonds can break. These bonds, ethyl hydrazone bonds can break, and include and incorporate the hard monomers. What happens then? What happens if you incorporate 25% of the hard monomers, the harder monomers, I should say, then your film is looking better already. If you incorporate 50%, you see that now the film is resistant enough not to bend, is stiff enough not to bend anymore under the weight, its own weight. And of course, you can go to higher, even 75%. You keep plasticity, but it gets stronger and stronger. So one can convert a soft and stretchy film into a hard and tough film by simple modification, by incorporation, dynamic incorporation of other monomers. Now let's look at some optical properties. Optical properties are, of course, quite interesting because you will see something. We hope to see something. And of course, that is quite convincing then when you see it. So let's do the following. We have again 2 films, AB and A prime B prime. We superimpose them by a corner here. And now we let it exchange. So the place where it is superimposed, but only there, the new combinations can be formed. A can combine with B prime, and A prime can combine with B. If one of these 2 new combinations has a color or a fluorescence, then at that place where it is superimposed, you will see a color and a fluorescence. So my Japanese co-workers made this little picture, the head of a cat, where the head is polymer AB and the ears also polymer AB. The inside of the ears, the eyes and the mustache is polymer A prime, B prime. They are superimposed here in this little picture. And now you let it go, you heat it a bit to get it quicker. And you can see that yellow color appears where superimposed and not elsewhere. And similarly, fluorescence appears where superimposed. So this is a very clear demonstration of the dynamic properties of this type of compounds, where the exchange occurs and generates this new property, which was not present at the start. A Diels-Alder reaction is especially interesting because it's one of those reactions where you do not lose anything. When you make a polyimine, you make the imine double bond and then you lose water. Of course, the interest in that case is that when you add water, you can hydrolyze it. So this is why it's degradable in the environment. Diels-Alder is a different story, because if you can find a Diels-Alder which is nicely reversible, we have found one which is a rather exotic type of Diels-Alder between a dialkyl fulvene and dicyanoethylenes here. But interesting, this is a very interesting compound, which this Diels-Alder was not known. You see that at 25 degrees, the Diels-Alder goes back and forth, back and forth, back and forth. It's like a chemical equilibrium, but it's a reactional equilibrium. Huh? One should notice that it's a reactional equilibrium. It's not a chemical equilibrium. So, not a chemical equilibrium like the binding of a midline, for instance. So then we can make monomers, which have a one monomer has at each end cyanoethylenes. Another monomer has fulvenes at each end, as shown here. You mix them, and you get then a polymeric entity where the polymer is formed by polymerization between the cyanoethylenes and the fulvenes, and this gives then connections through Diels-Alder reactions. And you note, because at 25 degrees it's perfectly reversible, these things here in this film, they open and close all the time. They are opening and closing all the time, which is in itself a rather interesting polymer. It's a polymer where inside the polymer things are always moving, going up, and it's really a living polymer. Not in the sense of a living polymer where you make synthesis, but it's very close to it. It's even, I would say, more living, because the structure of the polymer, even when it is formed, is all the time dissociating and reforming. So we can then do this. This is the reaction, this is the polymer, and we have now a film here. You can see here. You can cut it in two, and you superimpose the two pieces, the two halves. You press here with your fingers, and you can stretch, and it sticks. So here also is a case where the polymer is repairing itself after having been cut into two pieces. But now here it is not by supramolecular interactions that the polymer is reconstituted. It is thanks to the dynamic Diels-Alder reaction. Now, what about adaptation? Let's have a look at what adaptation means really. So for the moment, I've just shown that these systems are dynamic. Now, how can they change? How can they adapt? What are the features which can then be brought about and can be studied? Adaptation means that the system will respond to changes in the environment, phase changes, physical effectors, for instance, heat or pressure, chemical effectors like protons or midlines or other molecules, and even change of shape, but I will not talk about that. So this will be adaptive nanostructures. Let's look at the first case of adaptive self-assembly. It's a rather interesting case, although it looks trivial, but it is not so trivial. This compound has two bipyridines and phenyl rings. If you treat it with copper-1 in acetonitrile solution, you can see by NMR that you have three species present which are in equilibrium. You have a helicate, that means a double helix with two centers. You have a triangle, and you have a grid. So the mixing of these two produces three outcomes: double helix, triangle, and grid. And then you do something which seems very classical. You just try to crystallize it. Now, in a normal crystallization, where you want to separate a compound A from a compound B, if A crystallizes, B remains in solution. Now, in this case, it is very different. Indeed, the helicate, the double helix crystallizes. Here you see it. That's the double helix, which crystallizes, crystal structure determined and all that. So we know that it is the correct compound. But you understand very easily that as the helicate progressively crystallizes, the equilibrium in solution is always restored. So as the helicate crystallizes, it is regenerated in solution from the other constituents which are still there. And so you have more and more and more helicate, which is depositing, and in the solution you have nothing left because everything in the solution transforms into the helicate. It's so therefore very different from a normal crystallization, which is used to purify mixtures. It's a self-organization which is induced by the fact that that one of the compounds goes into the solid state. It's sort of a phase separation, if you want. Now, yesterday was asked the question about whether or not supramolecular systems can also be modified by redox reactions. That is why I added this slide here, just to show the following. That taking ligand on the left-hand side here, ligand number 1, this one which has a phenyl group, taking this ligand, mixing in copper 1, one gets a double helix. If one then oxidizes that with electrochemically, you get copper 2, which forms the grid. Copper 1 forms a double helix, copper 2 forms a grid. And this can be done reversibly. If you reduce or oxidize, you get you get a shifting, a switching between a grid unit for copper 2 and a base double helix unit for copper 1. So that's a nice illustration of how you can switch electrochemically and where the system adapts to the oxidation state of the metal. Copper 2, of course, does not give, the copper 1 gives a tetrahedral binding, and copper 2 prefers by far a tetrahedral, octahedral rather than tetrahedral. Now, let's see the adaptation to the medium. This is quite a striking example. We start with carbazole, with a long chain on the nitrogen here and 2 aldehydes. The core of carbazole is very hydrophobic. So what will happen with this compound is very hydrophobic because it has a chain of hexaglyme here. It is water soluble despite the fact that it is hydrophobic. Now you take another component, which is complementary, which has NH2 groups at the end, and you mix the two. You mix the two and these two, and then you get a polymer, which is this polyacyl hydrazone, which results from the condensation of that NH2 with that CO. Okay? The shape of this polymer is a folded helical nanotube. Why is that the case? Because the hexaglyme chain gives him solubility in water. So we operate here in waters in aqueous solution. But in aqueous solution, hydrophobic effects want to be minimized. In other words, the contacts between water and hydrophobic groups are minimized. The way to minimize it in the structure is to put them all in the center. And if you put all these units, these carbazoles in the center, then you get a rod, and we're sticking out of the rod the hexaglyme chains. So this is in itself an interesting polymer, which I cannot describe more, but it has been described. We have described it in the literature. But let me show you now what you can do with this in hand. Suppose we start again with the same system, but we have at the beginning, we mix these two alone. Pardon, I'm going the wrong way. We take these two, which we have already seen, and we let it go. What we know is you will get this dynamic polymer, the helical rigid rod. And then we will ask a question to the system. We will ask the question now to decide what it prefers to polymerize, in which way it prefers to do that. Suppose we add now this derivative of benzene with the same group as here, as this derivative of carbazole. Now, before you add this, the system is the same as previously, and you get this helical rigid rod. When you add this, then this unit with a smaller hydrophobic core is of course less subject to hydrophobic effects. So what you get is just the same. And so you can ask the question, so what? What do you want to demonstrate? What we want to demonstrate is that when you then progressively go from pure water to mixtures of acetonitrile and water, you convert a pure aqueous solution to an organoaqueous solution progressively. And as it becomes more organic with 80% acetonitrile, then you have a random incorporation of these two units. In other words, there is no hydrophobic effect anymore to drive the selection in favor of the carbazole unit, but you can now get mixed random incorporation of carbazole and phenyl rings into the polymer. Another case, so this is a clear demonstration of hydrophobically driven monomer selection. Now let's look at another one. This was work done with the group of Professor Paolo Samori, who is doing nanochemistry in our institute. And the experiment was the following. You take this long chain aldehyde and you mix it with 3 diamines, one with 2 carbons, 6 carbons, and 12 carbons. So this is now, okay, this can be looked at, this can be investigated by NMR. If you look at the solution in phenyloctane, you see by NMR that you have a very incomplete situation where you get monoimines, a mixture of the monoimines of the C2, the C6, and the C12. So that is not very informative. But then you deposit it on the surface of graphite. When you do that, this compound becomes deposits, and you find that the deposit is now a fully formed diimine, not just a monoimine, but a diimine, and only one of them. In other words, a simple adsorption on the surface has driven the reaction to completion, and the interactions, the compound have been selected. In other words, the adsorption drives the reaction to the PCMine and drives also the selection of that component which leads to the best deposition. That means thermodynamically is the most stable, and that is uracil. That is the C12 type of chain. This is interesting because it's an adaptation to surface adsorption. And what it demonstrates is it's similar to what I showed at the beginning with this crystallization of the mixture of double helix, a triangle, and a grid. But it is very informative and very convincing because you see here that the simple deposition on a surface can lead to produce a more complete reaction and to this is also then a way to select, and you can even say that it has a sort of a I come back to that later. There's sort of a contribution to complexification of matter as matter evolves from non-living to living. I do not claim, of course, that is evident, that these compounds are part of the origin of life. No, but the principle, the process is one of that type. And I come back to that because I find it is very important. Now, we have also studied different systems where you have adaptation in different types of dynamic systems. Let me just be a little bit quicker here. If you have this unit here, which is, this has aldehydes in these positions. These are functional groups here, aldehydes. They can condense with diamines, and then they get a polymer with no selection, an oligomeric polymer. If you treat it with a metal ion, you can transform this W unit, this is a W, to a U unit, and now you can have a combination with one of a more selective combination with one of the diamines, that's metalloselection. And if you shine light on it, you can change the configuration here of this imine bond, and then you have a new, and you have a switch, you have a new shape, and now this leads to photoselection. So this can be illustrated. I just will show you that quickly. It can, of course, you can go directly from one to the other, also you don't need to start from the beginning. Now, let me stress just that metalloselection and the absence of selection is this happens at the equilibrium, and photoselection is an out of equilibrium system, because here we have now light has been used to change the shape into a form which is not the most stable one. So this will slowly go back. Now this has been illustrated and in the following way. Let me just show you that quickly. So this is dialdehyde at the start in a W form. We mix in 4 diamines with an oxygen, with C7, with N with 2 oxygens, and with another diamine here. When we have just at the beginning, you mix together, you get no selection, you get a mixture of linear and cyclic oligomers. Now, when you add lead, you bend it around, the lead forms a complex, and now you have a single compound formed, which is the single compound derived from the diamine. Okay. And so this is now metalloselection. On the other hand, when you shine light, you change the configuration and you get now photoselection. Again, like I showed on the schematic picture, you can interconvert that by adding, for instance, lead or by shining light. So this is a case where you have a constitutional adaptation in a 3-state system. In absence of any additive, it's oligomeric, you have no selection, it's just a random formation of polymers. When you add metal ions, then you can select for the entity which has the strongest metal ion binding, and then the original selection of the photoselection leads to this, this single compound, where now it's a C7. This compound here is the C7 diamine. Where is it here? This diamine, which forms imines. This is at equilibrium, and this is out of equilibrium because it has been obtained under light. Now, let's analyze these complex systems, and this is an important point on which I want to finish, but we are not yet there, but this is the last chapter, which is of interest, and is extending the view one has of these systems into considering them as complex systems. You note that when you have a library of exchanging components, if one of them, if something happens to one of them, the other ones will know it because there will be a redistribution. So let's have a look how we can define a network. And I take the simplest network. You have A and A prime, which can react with B and B prime, the same nomenclature I already used, forming AB, AB prime, A prime B, and A prime B prime. Okay, now these are four constituents. The graph, which represents the network, is a square. And at the corners of the square, you have AB, AB prime, A prime B prime, and A prime B. This is the square. Now, on the edges of the square, the constituents share a component. They have a component in common. AB shares A with AB prime and shares B with A prime B. This is the point which I want to make, that this is now, because they share components, if AB increases, necessarily AB prime and A prime B will decrease. Of course, it's a contained system, a closed system, so that if you are able in some way to increase AB, AB prime and A prime B must decrease. And what happens then? If AB prime and A prime B form AB, then of course they liberate A prime and B prime. And this A prime and B prime can form A prime B prime. So on the units, the ones on the edges, they are in antagonistic relationship. When one increases AB, then the other ones must decrease. But the agonists, they are very different. The ones on the diagonal are agonistic, which means that they work the same way. If AB increases, A prime, B prime also increases, because when AB increases, it increases by forming AB from AB prime and A prime B, so that A prime and B prime can form more A prime, B prime. Okay, I suppose it's clear that on the edges you have antagonists which work in opposite directions, which change in opposite directions, whereas on the diagonals you have agonists which go in the same direction. They go both up or down. So the important thing here is, and this will come up later on again, is that you have agonist amplification. When one agonist, for instance, AB, is amplified, increased, it also increases A prime, B prime. So the fittest drives the amplification of the unfittest. This is a very interesting property. When constituents do not share a component, they are agonistic. And this, of course, is rather intriguing, that the fittest for a given property drives amplifications of the unfittest for that same property. And these are adaptive chemical networks. Let me illustrate that now in a very simple way. Take this pyridinaldehyde and benzaldehyde. Take this hydrazide and the N-methyl hydrazide here. They can make four constituents: AB, AB prime, A prime B, and A prime B prime. These are the four constituents you can obtain. Now, what can we do with those? If we start with these four constituents, we make them and then we mix them. Now, if we add a metal ion, a metal cation, for instance, a metal cation M, in presence with a weak base, which is the best ligand? NO is very good as a ligand combination. In addition, the H can be ionized by weak base and triethylamine, so that you generate a negative charge here, which further stabilizes the complex. And indeed, when you add an effector metal, you should get this complex with an amplification of AB and also amplification of A prime B prime. And this considered amplification is driven by the metal ion for instance, zinc. So we can represent this by networks. Here is the network. We add the zinc. It amplifies the AB very strongly, which amplifies A prime, B prime, and the other two, in fact, have disappeared almost completely. This is adaptation of the system. And again, we have agonist amplification. AB, the best ligand for zinc, is amplified strongly, which then has as consequence that its agonist, A prime, B prime, is also amplified. And the agonist, A prime, B prime, is the unfittest, the least good, the less good ligand for binding zinc. So it is clear demonstration that the fittest, in this case for zinc binding, amplifies also the unfittest, in this case for zinc binding. So it's for zinc binding that it is the case. But you know, what is interesting also is that if you amplify the unfittest, and for instance, and we have cases like that, where if the unfittest has a color, then you will amplify the color simply by acting on AB. In other words, you don't have to amplify AB, A prime, B prime itself, but you, by acting on AB and increasing the percentage of AB, you will at the same time amplify A prime, B prime. Now, this is now a more complicated thing, and we'll not go too fast. We have still some time, but it is very interesting because of the lessons we get out of it. Again, it deals with metal ions and ligands, because metal ions and ligands are a rather simple way compared to molecules for studying these kind of features. Suppose now we mix 3 aldehydes and 3 amines. 3 times 3, these are 9 constituents. So you mix them and you look what happens. What happens is not very interesting. It's even rather boring. It's an incomplete setup where there are some imines have formed, then the imine D4 is free and has done nothing. This one has done nothing. That is quite easy to understand, that an amine on a quinoline is already partially deactivated because it is the nitrogen, the amine is less basic. Then you see here that, for instance, there is no combination of A6 and D4, A7 D4, E4 D4, no combination. That means you have just free DA. There's free DA because it does D4 does not want to react with any of the A's because this nitrogen is not a very basic one, not a good nucleophile. The others react a little bit, somewhat more or less. Okay. Now you add air, you add copper 2 to this. When you add copper 2, you add copper 1, excuse me. You add copper 1 to this. Now, copper 1 is easily oxidizable at air. And copper 2 can make a very good complex with the aminoquinoline D4. So when you add copper 1, the network is distracted and you get just a complex of copper 2 with the quinoline D4. This is not interesting at all. But then we can do the following. We start by adding iron. When we start by adding iron, we observe that iron makes a very good complex with the combination of A6 and D4. That means this pyridinaldehyde and the quinoline. So this is strongly amplified. And at the same time, there is now an agonist, which is not one compound, but here, since we have 9 constituents, this is now a network. The 2x2 network is amplified by the formation of the iron complex with aminoquinoline. Okay, so that is one step. But now you can add to this also, where is it? You can add copper 1. And if you add copper 1, then you find out that now you have a very strong simplification of the whole system. Copper 1 can now operate on this sub-network shown here and make it express copper, this is copper 1, and make it express the copper complex, the copper 1 complex, which is D3A7. And this is shown here, the copper 1 complex. In this case, what you observe are two important things. The system is not oxidized anymore, copper 1 to copper 2, and you have greatly simplified the network. You have only one diagonal left. See, this is only one diagonal of ligands, of complexes, not of complexes, I should say, of an iron complex, a copper complex, and the last one, which was just remaining. Now, what does that teach us? We can, of course, also add directly copper 1 and iron to this, and you get also the same. First of all, there are two levels of agonistic amplification. The first is iron amplifies the subnetwork here, and then copper amplifies this diagonal in this network. You may note that even this network was not really preferred at the beginning, before you had copper 1. So you have also a network switching from here diagonal to this diagonal. So, second point, there is a conditional response. It only works, it only responds when there is a sequence and the correct sequence. You first have to add iron, and then you can add copper 1. Otherwise, it's destroyed. There is an increase in complexity when you add one more entity. In other words, as I said, you start with iron in the system, and then you add one more. With iron, you have this thing up here. When you add then copper 1, you get a simpler result, despite the fact that you have increased it by one component. You add one more thing, and the output is cleaner, simpler. So that means increase in complexity can lead to simpler output, which you can call simplexity. So step 1, adaptation to effector 1, iron. Step 2, adaptation to effector 2, copper 1. And what is important here, you conserve the adapted features. What I want here, this is of course, it's a bit, it's not it's a very simplified demonstration, but what I mean by that it is that two sequential adaptation steps, and the second step builds on the first one. The first one adapts to effector iron. The second one adapts to copper, but this adaptation to copper takes advantage of the fact that iron has already done an adaptation. So that is more an evolution than an adaptation, because by adding iron, you prepare the system to the next step. So it's an evolution of the system. Okay, I hope I have insisted on that because I feel it's quite important. And now we will see something else which is of interesting. Can self-organization, that means the generation of a more organized state of matter, lead to the selection of given components, and which we will see. So it is known that guanosines can form supramolecular macrocycles. These are guanine quartets. This is well known. G quartets are very well known units, which also exist at the ends of the chromosomes. At the end of the chromosomes, they can form G quartets. This is well established. This is very well known in biology and genetics and all that. So guanosine does that. Guanosine is the one where there's CH2H here. But then one can modify guanosine and make guanosine 5-hydrazate, which has a CONH-NH2 here. If you add sodium, potassium, or ammonium to that, you get this guanine quartet, the supramolecular macrocycle, which then, in presence of the metal ions, stacks and yields this kind of stacking, which is a gel. This stacking is a gel, this entity. And here you see it, the gel in sodium acetate, and then which can be shown to by them pictures to have fibers and so on. So this guanosine hydrazate, on addition of especially potassium, leads to this gel. So that is the starting point. Formation of an organized state, because a gel is, of course, more organized than a solution. So let's analyze this gel formation. It presents 3 dynamic steps. First of all, the formation of the G quartet, the guanine quartet, this macrocycle, supramolecular macrocycle with 4 quartet units, is a first step. It's a non-covalent organic dynamic system through hydrogen bonding. It's supramolecular dynamics. Then you add the metal ion. The metal ion introduces now inorganic dynamics because the metal ion can bind or can be removed. So it is also complexation, decomplexation, complexation, and so on. And finally, you can, once you have obtained that, you can also react an aldehyde with the NH2 here, which is on the exterior of this type of macrocycle. And this can then lead to a change in the properties of the resulting gel. So, as I said, this is a gel, and the properties of this gel will depend on the nature of the aldehyde, which is used to decorate the outside. This is now a reversible decoration with aldehydes. This is a reversible imine formation. Then by investigating different types of aldehydes, we found out that some of them, some aldehydes, like the benzaldehyde, disulfonic benzaldehyde, or the monosulfonate, they transform the gel into a solution. In other words, if at a given temperature, at a given concentration, you get a gel, the addition of these sulfonamides, making this outside imines here, makes the gel dissolve. That means transforms the gel into a solution. On the other hand, these 2 aldehydes I show you here, and especially pyridoxal phosphate, which is the group which is present in the enzymes, transaminase enzymes. So it's a prosthetic group of enzymes, of the transaminase enzymes, but this is irrelevant here. We just use it because it has also negative charges, it makes water solubility, and so when you condense the initial unit with the 4 amines at the end, you decorate it with pyridoxal phosphate, then you get a stronger gel. Now, what is a stronger, better gel? It's a gel which melts at a higher temperature. The temperature of melting of the gel, the transformation of the gel into a sol occurs at higher temperature. Okay, now we can set up a system where we can test a property, the effect of the formation of a gel on the selection of, or the amplification of the compounds. Let's start with 2 hydrazides. One is the guanosine hydrazide, which can form, as you have shown, this G quartet, this supramolecular macrocycle. And on the other hand, the hydrazide of serine, which cannot form a macrocycle. And then we can add the sulfobenzaldehyde, sulfonated benzaldehyde, which we know has a tendency to transform the gel into a solution. That means making the gel less stable by decoration. And pyridoxal phosphate, which does the reverse. Pyridoxal phosphate stabilizes the gel, and that means it has a better organization. So then what happens? You just mix this, and then you analyze the resulting mixture. How can you analyze it? First of all, it forms a gel. When you mix this at 15 millimolar in a 0.5 sodium acetate buffer, you get then you get a gel. Now, this gel can be analyzed by NMR, but you know very well that the gel will not show NMR signals because it's very broad. However, those components which are not in the gel, they will be seen by NMR. So, in the water included in the gel, you find those compounds which are not part of the gel itself. AB prime, A prime B prime, and A prime B. You note here that these are compounds which are either cannot form a G quartet, or where the one which can form a G quartet is now connected, decorated by the sulfonate, the sulfobenzaldehyde, which we know has a tendency to destroy the gel. So, by difference, the gel must be the following. The gel must have the guanine in order to form the macrocycle, the supramolecular macrocycle, and it must contain the pyridoxal phosphate, which is indeed the case. You see, the pyridoxal phosphate is not present here. It's not present in these two, of course. It is present in this one, but this one cannot form a G quartet. So this cannot form a gel, and this cannot form gels either. The gel is entirely constituted of AB. If you now look at the distribution, the gelification, the formation of the gel, has enforced the distribution to form AB and A prime B prime, about 40%, and 10% of each of the other two. These are agonists. AB and A prime B prime are agonists. So they are amplified. And of course, AB prime and A prime B are also agonists, but they are reduced. So the AB prime and A prime B go the same way down, and AB and A prime B prime go up, both of them. Amplification of constituent AB has occurred. It is the constituent which leads to gel formation. And at the same time, of course, it amplifies A prime B prime, which is the agonist of AB. Now, what does that mean? That means that the formation of the gel has selected among the constituents that constituent which leads to the best gel. And so the gelation driving force can be obtained by this ratio here, and there's a selection under self-organization pressure. The fact that you can self-organize leads to the selection of what leads to the best self-organizing unit. Yes, I want to accelerate a little. So this is just representing the same thing in this schematic way. And we can have then this network representation, self-organization driven, and then you have an amplification of AB and A prime in the gel. Adaptation to gel formation, selection and adaptation under the formation of a self-organized entity. The fittest amplifies the unfittest. Here, the fittest is the one which gives the best gel, and the unfittest is the one which does not want at all to form a gel. And this is very significant for the prebiotic evolution of matter. And I want to show you that, wait a minute, this is a bit complicated. Okay, nevertheless, let me show you. We had found that this Gneuenagel compound undergoes an exchange reaction, an organometastasis, through a four-membrane. And so that you can then build up a system where you have an exchange between R2 and between these two units, and R1 and R2. Oh, there's this should be R1 here. Huh? This should be R1. And so you can get then these two derivatives, which can form also a rosette with 1, 2, 3, 4, 5, 6, not G quartet. It's a hexamer macrocycle, which can then form a column, a supramolecular polymer. And this is a very strong supramolecular polymer forming unit. So at the beginning, you have here an exchange reaction, which can exchange the two units. One of them has a good, as a tail formation property, but it has to pass through the rosette formation. And then after this rosette formation, you can get the supramolecular polymer gel. Now, what happens then is the following. You can study the line width. The NMR is here very, very informative, because when the line width increases, it means that it is more viscous. And that is the interesting thing in NMR, that the viscosity is directly measured by the line width of the NMR signals. But let me not insist on that, because it's a long story. I want just to show one thing, the following. When you use, of course, when you change the solvent, you can dissolve it more or less. This is that's quite evident. But suppose we fix ourselves at a mixture of 30% chloroform and 70% deuterated cyclohexane. At high temperature, a high temperature means 343 K, this is a solution. And you see that the four possibilities, which are shown here, these four possibilities up there, you distinguish them by the color. The four constituents are about 25%. It's a statistical distribution of these four constituents. Then you drop the temperature to 293. At that temperature, now the gel has formed. And you see that there's now an enormous amplification of the ones which form a gel. And the ones which forms a gel here is the KN3, the constituent which has a naphthalene and this long chain here with C3CH, C12H25, these units. So this clearly demonstrates that the formation of a gel by this derivative here leads the system to generate more of this derivative. At the beginning, it's only 25%. And when the gel is formed, then the other ones have lost their components, which lead to the formation of KN3 and of A1, and then lead to this amplification of the two agonists. The effect is very strong here, and it's a stronger a stronger driving force for forming the selection. Now, I here represent that in a picture. This picture is, you shouldn't consider it as it's not very complicated, but it gives us the result, and the result is what counts. When you are in conditions where the system is a solution, then you have statistical distribution of the four constituents. When you then cool down and go to the state of the system where it has become a gel, then you strongly amplify the supramolecular polymer, this one, which forms the gel. if we summarize this, it means that there is self-amplification of organization. In other words, the system prefers to make that constituent which makes the gel. So it's the formation of the gel which drives the system. And that is something which I feel is very important in the generation of order as matter becomes more complex. Yeah, now this is a bit long. I need to accelerate. Let me just show you the one system also where you can adapt to reversible phase separation. It is quite interesting. If you start from a system which is homogeneous and where you distribute the constituents in not exactly statistical fashion because one is a bit preferred over the other one, then you can separate this homogeneous system is constituted of a solution of these 4 constituents in acetonitrile water 60-40. Then you add an effector which separates the 2 phases. And then you have to redistribute the constituents. This can happen with sodium chloride. With sodium chloride, you have a phase separation. And you see that now the more lipophilic unit, which is this one here, which has lipophilic groups, is now amplified in the top, in the organic layer. And the other one is amplified in the bottom layer. This one, which is soluble in water, is amplified in the bottom layer. So the simple separation of a homogeneous medium into 2 compartments, that is important also because compartmentalization is an important feature to make more and more complex states of matter. So you select you redistribute the constituents so as to select and amplify the ones which are more organic, and the ones which are more aqueous. Now, here I would like to finish with this thing because it was also done by one of my co-workers who was of Ukrainian origin, Dr. Artem Osipenko. This being said, what I indicated here, you have now 2 phases. Now, suppose in these 2 phases, you now do a perturbation in one of the phases. What happens? Let me simplify in the following way. You start with 2 phases, and you have an equal distribution, more or less, initial distribution at the beginning between the 2 phases. In the out phase, suppose you are sitting down here in the out phase, and you look at the distribution of the entities which come down which distribute down here. Then you add effector 1. It will you add effector 1 into phase in phase, and it will modify the distribution so that the reading phase, the bottom phase, has a dynamic fingerprint, which is different from this distribution. And similarly, you have another distribution here when you add another effector. In other words, the addition of an effector into the in phase leads to an outcome in the out phase of different fingerprints for different effectors added in the top. What does that mean? That means that this is now a complicated thing, but I want just to show the result. The result here seen is the following. We have at the beginning distributed, you see down here you see here, we have distributed these compounds, these constituents, components and constituents, all of them. There are 4 constituents and there are 4 components. They are distributed between the 2 phases. Here we have chloroform, so the water layer is on top, the chloroform layer is on bottom. And what you see, in absence of any addition, you have more or less statistical distribution on the right. But then, when you add different metal ions, manganese, iron, cobalt, nickel, copper 1, copper 2, zinc 2, cadmium 2, lead, and palladium, you get now this, you add this to the top water phase, and then you get a distribution, a fingerprint in the bottom phase, which is characteristic to what you have added on the top. So the distribution indicates the distribution in the bottom phase, where the metal ion cannot go because it's chloroform. Nevertheless, that distribution indicates what has been added in the top. And this is then represented in the following way. You start with a square in the homogeneous medium. Then you separate into two phases. That is what we have, the top phase and the bottom phase. Organic is chloroform in this case, aqueous phase. And this then leads to the changes, the connections between the two phases. The agonist amplification now occurs between the phases and not the same. You see that when you have a single phase, agonist amplification is on the diagonal in the single phase. When you now have a splitting, you get a square prism, and now the agonist amplification occurs between the phases, from one compartment to the other one. The same, then of course you have also agonist repression in the same unit. But the important thing is this: when you now add an effector, which we have just done, when you add this, when you add the effector, then you see that you have the distribution of what is seen, the fingerprint, which is distributed into the organic phase, tells you what has been added in the top phase. That means that information is in a distribution. It is not in a single molecule constituent. It is in a distribution. It's a distribution which tells you what has been added. And this is what is shown here in this complicated diagram. But these all change depending on what is added, and the distribution of the constituent and components indicates what has been added in the other compartment. So even if you do not know what has been added, if you do not go there, you cannot go there. Nevertheless, it's seen through the distribution. Okay, I think in view of the time, I will, I wanted just to show, we can also train the system. Let me just show you the principle, not giving you the details later on. Suppose you have AA prime, BB prime. I always use this same representation. And if AB combines, you form a sort of a hexagonal cavity. If A combines with B prime, you form a square cavity, and the other ones form other shapes. Okay, so you mix this together, these compounds. And then you choose a reaction which is kinetically slow. I insist on that. All the others we wanted kinetically fast. Here it's kinetically slow. So you now add something which of course can be a metal ion which wants hexa coordination. And then you train your system, you change it progressively to a new distribution which is imprinted by what you have added. This is, and then you get this new distribution. Then you can add here a ligand which binds this yellow unit better than AB. So this is removed, but because the kinetics are slow, right after the removal of the imprinter, the distribution does not change. It will change slowly with kinetics, at the rate of the kinetics, but not fast. So the distribution is prepared for what? Prepared for the recognition, for recognizing, for remembering that it has been in contact with this yellow unit. So the other side is just the same, so I want to insist on this side. The system at the start is more or less statistical. It is trained by slow changing the distributions to amplifying the unit which binds this and its agonist. Then if this is removed, because the kinetics of dissociation and formation of these constituents is now slow, the system retains the same distribution enforced by the imprinting step. If then it is put in contact again with the same entity as the imprinter, then immediately it is recalled because the system is already in the state where that unit can be recognized. The same is true for tetrahedral recognition. So I don't want to insist on this, but I want just to indicate that at the beginning, you have the equilibrium state. Then you use imprinters, either hexagon or square, and this then changes the distribution in the system to new distributions, and these are out of equilibrium states. These are memory states. As you know, memory is an out of equilibrium state. In our brain, memory means that the brain is not at equilibrium. It is, and the memory can be lost, but also memory means also that when the same thing comes back, it will be remembered. When the same object you have seen something around you, then you go to another room and you come back to the same room and you recognize what you have seen before. So that is a memory state. Let me not go into the details because this is just demonstrating with metal complexes that it works. So this is again memory. So let me summarize quickly. The adaptive chemistry I have described has a number of features, and I just go through them. It operates as a dynamic network. That means where constitutions can change dynamically depending on what happens to the system. Then there's a response in the distribution of constitutions, in a response to the addition of given agents, physical or chemical. Self-organization it can drive adaptation. When self-organization can occur, then the system will adapt to the formation, to the fact that it can self-organize. Agonist amplification means that the fittest can amplify the unfittest. An increase in complexity, that means adding one more effector or even more than that, leads to a simpler output, which you may call simplexity. Information processing occurs in a constitutional dynamic distribution. You can store information, you can imprint it, and then recall when the imprinted distribution is put again in contact with what the imprinter was, and you can generate out of equilibrium systems. So I have been a little bit faster at the end because I saw that I couldn't maybe finish in good time, but I hope to have shown you that indeed these systems have a lot of interesting features. They are sort of complicated sometimes, but of course, for the moment I have selected, and we have mostly worked on simplest systems which have 4 components and 4 constituents, except for one, which had 6 components and 9 constituents. But this can be also extended, but then when it becomes much more complicated with many more components and constituents, one has to treat it mathematically, otherwise it's not possible. You have no representations anymore. It becomes a multi-dimensional space. So we have started in molecular chemistry, supramolecular organized. Then it has to be dynamic if one wants to go further and to adapt, adaptive, and so that there's ways towards more and more complex states of matter. Let me say that by the things which I find most important here is that the increase in complexity can lead to simplicity, that agonist amplification leads to the fact that the fittest entity for doing something amplifies the unfittest for doing that thing, but it can do something else. And finally, perhaps the most important in terms of general principle is that when a system of dynamic nature can form an organized state, it will generate that entity which leads to the organization. So it's a self-catalysis of organization. And I think that is a driving force in the development of complex matter. So thank you very much for listening. I am at the end a bit fast, but I hope you nevertheless have gotten something out of it. And some of those things are published, so the papers are available. And I would like to thank you for the invitation. I would like also to wish you good luck for the days which are not simple and which are very complex for you. And I hope that the situation will get better. We all hope that. We all hope that these crazy events, this is really absolutely incredible. But all my best wishes to all of you. Thank you very much.
Thank you for your very nice talk and for rather complicated things which you showed us today in your lecture. I hope we have some time for questions.
Yes, we have about, let's say, 20 minutes, 15, 20 minutes.
Yeah, okay. Dear colleagues, we have about 15 minutes for questions. If you have any question, please, you can start your discussion.
Можно?
Of course.
Да. My name is Victor Kuzmin. I am from Odessa. I'm pleasure to remember our meetings in Odessa and Strasbourg.
Yes, that is true. Yes, I remember that. I also remember. Wait a minute. What was the name again of the organic chemist there?
Yes.
Who came to Strasbourg? In Odessa.
Odessa, tak.
No, an organic chemist who came also here.
Bogatsky. No?
Bogatsky, yeah, that's it. That's it.
Yeah,
exactly. Thank you, Bogatsky.
Thank you. My question. Thank you very much for very interesting lections. My question about supramolecular helixes. I think in all cases, racemate should be formed, left and right helixes. Is it possible to carry out such a synthesis stereoselectively? Obviously, this requires chiral ligand. Do you know such examples?
Yes, in fact, we have done it. You are totally right, and this is a very good question because indeed the helicates, they are a mixture of racemic compounds.
Yes.
But we have then make a ligand which has a chiral center at the end, of the chain, and then you get only one enantiomer.
Mm-hmm. Thank you very much.
Thank you for the question. That's true.
Thank you for your question, dear colleagues. More question for discussion. Please don't hesitate. Okay, my question is about dynamic libraries for biological active compounds via the receptor. So yes, in my lecture for students, I showed this example of dynamic libraries, but do you know any successful example of application of this strategy for searching of drugs in practice?
Not in a company, we had a small company where we had cases like that, but that was never published. The point is, I think the following. nowadays, companies have been, let me say, these dynamic systems that generate a lot of complexity, and then you have to analyze it.
Yeah.
Nowadays, what companies usually do, they have very large non-dynamic libraries, but they have very fast robotics to analyze them. So you can do extremely fast screening of many compounds.
Yeah, high throughput screening. Yeah, I understand it.
High throughput screening, yes.
Yeah.
Whereas in our case, of course, the compounds are produced in a dynamic fashion, but then you have to screen them. And one way of doing it is to, for instance, if there are imines, you can reduce the imine bonds into amines, then they are stable, and then you can analyze them. Mm-hmm. But it is, for the moment, there has been no case where it has been used. I cannot know that because maybe they have used it, but there is no, let's say, successful case which has been published where the dynamic approach, which in principle should be almost ideal because of this automatic generation of a high diversity, but the deconvolution is the problem. And we have done that by this dynamic deconvolution, which I have mentioned. But I think also that the companies are now so well equipped with high throughput screening for screening processes that they don't want to change, because it would be a change to go now to dynamic processes. But it could be interesting for many other things, not necessarily for making drugs, but it could be interesting for generating colors, for generating different optical properties, and so on.
Yeah. You showed some examples here, very interesting. Yeah, and maybe the next question is about dynamics networks, and your case of Sol-Gel methodology with application of metal ions. So yes, through the complexation, you go to simplification, and for gel you need only AB, but you also amplify A prime B prime.
Yes.
Is it possible to simplify more and exclude A prime B prime from amplification to obtain only AB that you need for gel?
The fact is that if you everything
completely selective process.
Yeah, that's a good question. But it's automatically you form the agonist automatically when the antagonist formed. You form the other agonist when you make the first one. If one agonist forms a gel, you also form the one which does not form the gel. That is the principle of the networks. Because the network is now, of course, you may be right. If the network is not a closed space but an open space, then it may be. For instance, let me just say that one case, a simple case, very simple case would be that if you make imines, then you make water. And if you dry the system, it will amplify the ones which are the less soluble. But of course, the other one will not go away unless it evaporates. But one can imagine systems where one agonist is not evaporating and the other one can evaporate. That would be one.
Or maybe a solubility of your agonists.
Absolutely, that one of them precipitates. The agonist one of them precipitates. Yeah.
Okay.
This is something which I was too fast, but when you phase separate, the phase separation cases at the end where I was a bit quick. In the phase separation cases, when you do it many times, then you add salts. But if you use salts which undergo double decomposition, you see these salts which are classically form you have two soluble salts. You know that this is very classical. Two soluble salts, you mix them and you get two precipitates, because when the salts exchange their anions and cations, each of them now precipitates separately. So in that case, you can possibly induce precipitation of one of the constituents.
Okay. So we have a question in chat from Volodymyr Farafonov from Kharkiv National University. First of all, thank you for facilitating horizontal wedding lectures. I am wondering about the effect of external energy flows on such reaction networks. I am asking in the relation with works of Jeremy England, which are rather known in the community of researchers of the origin of life. He theoretically showed that in non-equilibrium conditions, reaction networks spontaneously rearrange to consume the maximal energy. Did you observe such behavior in the experiments with component libraries?
No, we didn't look at it really, because it's true. Okay, I cannot do everything. So I am of course interested in out of equilibrium systems, but we did not look at energy consumption. And I was at this stage more interested in the possibility of showing that the existence of order favors those systems which lead to that order, with sort of this, as I said, the catalysis of self-organization. But we did not look at any of the physical-chemical properties of that. That's a very good point. It's something one should do, of course.
Okay. Thank you for the answer from Volodymyr Farafonov. So, dear colleagues, we have maybe about 5 minutes. If you have questions, please. Because in my opinion, it was very interesting materials, but maybe rather complicated for understanding quickly.
The thing is, if one is not in the field, it's sort of new and a specific field. So one has to be a bit accustomed to it, I guess. One should spend more time.
Yes, we will make a presentation of your lecture on our Facebook page, and many persons will look for your lecture and listen it. So, dear colleagues, if you don't have any question, I would like to thank Professor Jean-Marie Lehn. He's very, very busy person, and now he will go for another lecture. And he found a time for lectures for community of chemists in Ukraine, and it's support of Ukrainian chemists, of course. Thank you very much for your support, for your time, and for your efforts in science, and for your presentations.
It's my pleasure to have done it. And thank you for the invitation. And as I said, best wishes to all of you.
Thank you very much.
Okay.
So,
thank you.
Have a nice day. Thank you.
Bye-bye.
Bye.
Thank you. Goodbye. Have a good day, you too, over there. Bye-bye.